So I've been working in interpretable machine learning for, I can't even, over a decade. And so today I'm going to talk about two extremes, very, very sparse models, linear models with integer coefficients, and then interpretable deep neural networks for computer vision. So the two extremes. I just need to start with some definitions. I'm sure you've heard these several times today, but essentially an interpretable machine learning model is constrained. It obeys a domain-specific set of constraints so that a user can better understand it. And I have a technical definition that lists a bunch of these types of constraints that you might want to put in, like monotonicity, causality, or generative constraints, or whatever. Okay, and of course, there's a spectrum between machine learning models that are very, very sparse, where you can really understand how the variables are jointly working together to create a prediction. And then on the other end of the spectrum, models that are just loosely constrained to be like monotonically increasing along one variable or something like that. And so why do you need interpretability? And of course, we need them for high stakes decisions or for when you want to troubleshoot. So I've listed a bunch of applications there: criminal justice models, credit scoring, air pollution, airplane maintenance, biometrics, anything that's really high stakes where you don't want to make a mistake. All right, now, evidence does not support the interpretability accuracy trade-off. I know a lot of people would really like it to, and a lot of people really say it does, but it really doesn't. And people will go to great lengths to demonstrate that such a trade-off exists when it isn't there. And so I'm going to just talk a little bit about this image for a while. So this is from the DARPA Explainable AI BAA. And here it's supposed to show an inverse relationship between learning performance, so something like accuracy, and the effectiveness of an explanation. Now, the first thing that I noticed when I looked at this figure, which I found very disturbing, was that it's not real. There's no quantification of the axes. There's no data set that this corresponds to. This is just somebody who created this in PowerPoint. This is like President Trump with the Sharpie. It's like somebody drew it. There's nothing in this image. And so I was like, okay, well, hold on a second. Let's pretend that this actually was quantified. So what is it trying to show? It seems to be indicating that somebody tried a bunch of machine learning methods on a single data set and then plopped a bunch of points there, showing that as the model gets more accurate, it's less effective in terms of explanations, and as it becomes more interpretable, then it's less accurate. And I was thinking, but this looks like they're working with a static single data set and a fixed evaluation metric, but that's not the way we do things in data science. In data science, there's a pipeline where in any data science process, like the KDD process or the CRISP-DM process, you're supposed to interpret the results after you get them. And then the information you get by understanding what happened feeds back into improving the data set and improving your performance metric. And so the fact that you could actually understand what's going on helps you improve the whole process. So this idea of a static data set and fixed evaluation metric is simply wrong. And then also the trade-off doesn't happen like this, even if you had a static data set and a fixed evaluation metric. In most cases, in most tabular data sets, it's pretty flat. And if you're working with computer vision data sets, it's very different, but you can still get exactly the same learning performance with substantial explanation effectiveness, or whatever that means. So this trade-off really doesn't exist, even with a static data set and a fixed evaluation metric. And then also, this particular example didn't tell you whether they were talking about explaining black boxes or actually designing models that were inherently interpretable. Now, if you're explaining black box, fine, yeah, then it's approximation problem, and you're going to see a trade-off like this. But if you're actually trying to design a model that's inherently interpretable, there is no trade-off for every problem that I've ever seen. So, and it turns out that this particular image was supposed to represent explaining black boxes, and the author did not realize that there's a chasm between these two concepts. I'll talk more about that. Okay, so there's really two different kinds of problems. There's sort of tabular data where all the variables are real valued or categorical or binary. And I always end up with tabular. I don't know why, but somehow the problems I end up working on are there's always tabular data involved. But there's also raw data on the other hand, which is like image processing data or sound waves or large amounts of text, where in these types of raw data problems, like an individual pixel is not a good predictor of the outcome. And you really wouldn't want to look at an individual pixel by itself. It's not really meaningful as a feature. And you wouldn't want to create like a sparse model in pixel space. It doesn't make any sense. So here, the definition of interpretability has to be different than what you would typically use over here, which would be kind of decision trees, models like that. So now for raw data, the only technique that's really working right now on these kind of raw data problems are deep neural networks. But that doesn't mean that they can't be interpretable. So I'll go through later some examples of interpretable deep learning models that are just as accurate as black box ones. But again, the definition of interpretability is kind of funky. Now for tabular data, with minor preprocessing, so as long as you're willing to do that level of preprocessing, you can pretty much always get the methods to have very similar performance. And that includes very sparse models like sparse decision trees and sparse scoring systems. And it's surprisingly true. Like, it's really hard to beat logistic regression models for a lot of tabular data problems. I even wrote a song recently called "I Can't Beat Logistic Regression." So it's kind of an interesting aspect of these tabular data sets. And this is why people for years were saying, like, we're overfitting the UCI machine learning repository. Like, we actually can't beat logistic regression. Now I say this, but then a lot of people say, but no, you're wrong. You must be losing accuracy because these models are constrained, right? When you add an additional constraint, it limits the flexibility of the model. And so it can't possibly be as accurate as the black box models. And you would think that black box models would be more accurate, but it's really not even usually the case. But it depends on your ability to choose a good definition of what interpretability means so that you can incorporate the constraints and effectively optimize that combination of the constraints and the accuracy or the performance metric. And in most cases, interpretability actually helps accuracy because you understand what you're doing and therefore can do a better job of it. So I'm going to give you an example where a lack of interpretability leads to errors in practice, and no amount of explaining your way out of a black box will actually help the problem. So this is an example of where a typographical error can lead to years of extra prison time. And in fact, it has for many people. And of course, this is the COMPASS example that I think you're probably all familiar with, where there's a black box model. It's used widely across the US criminal justice system, and it's used to deny people parole. Now here, this example is where someone was denied parole. This is a person who was in prison since he was a child. And then he was a model prisoner for some 17 years or something. He comes up for parole, it's denied. And he found out only afterward that it was because of a typo in his criminal history features, because he compared his score sheet with somebody else's score sheet. So he said, okay, I wonder if we actually need this black box model. And so at the time the Florida data set came out for COMPASS, we actually took the data and compared it with the latest machine learning method from our lab to see, do we actually need this black box? So we compared COMPASS with corals, which was our latest method that we derived in 2017. And in our 2017 paper, we took the Florida data, tried to predict outcomes, and we ended up with a model that fits in the bottom of a PowerPoint slide. So the model is really tiny, and it basically says, if you're young and male, predict that you'll be arrested within 2 years of your COMPASS score calculation. Else, if you're a little bit older and you have a couple of prior offenses, predict arrest within 2 years of your COMPASS score calculation. Or if you have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and thought, there is no way this thing can be as accurate as this fancy black box that's used in the justice system that uses 137 factors, most of which we don't even have. But we were wrong. So this is tenfold cross-validation accuracy for COMPASS and corals. The different colors are different folds of the data set, and they're about equally accurate. And not only that, We tried a whole bunch of other machine learning methods, just the whole, just send all of them in there, and they all were about equally accurate. And some of these are really black boxes like COMPASS, which is proprietary, but also boosted decision trees and support vector machines with radial basis function kernels and so on. And so we thought, okay, there was this huge debate about algorithmic fairness of COMPASS, but the truth is that we just don't seem to need COMPASS at all. Like we can get away with very simple models. So it's not clear why we're even still using COMPASS. I mean, I'm not saying that we should use this model, right? Obviously this model has issues, but I'm saying if that model can do well, there's, we don't need COMPASS, okay? We don't need to have typographical errors in people's scores causing problems. And again, no way of explaining COMPASS is going to get you out of this mess. Now, for many problems that I've worked on, for all of the ones that required interpretability, we were able to create a model that was interpretable at the same level of accuracy as black box. And when I say accuracy, I mean just sort of general performance measures. And I've worked on a lot of different applications, and here are some of them, all of which required interpretability. Okay, so what I've shown an example of is, the fact that for tabular data, we can often have very sparse models at the same level of accuracy as a black box. And so what I want to do is kind of harp on that a little bit more and talk about kind of how you construct these very sparse models and show an application where we do it. And then I'll switch over to the raw data problem and go to the other extreme. All right, so scoring systems are sparse linear models with integer coefficients. These kinds of models are used very, very heavily in medicine. So here's an example of one scoring system. It's called the 2 helps to B score. So why is it called that? Because it's 2 HELPS and then 2 points for the B. So the doctors can memorize the model just by knowing its name. And this particular model is designed for neurologists to use to predict seizures in patients who are in the intensive care units of hospitals who are at risk for brain seizures. So let me tell you a little bit more about that problem, and then I'll get back to the 2 helps to B score. So let's say that you have an aneurysm in your brain and it bursts. So what that means is you have a hemorrhage and there's blood actually in your brain. So this is a brain hemorrhage and the person has blood in their brain. And for these patients, they would get surgery and be placed in intensive care and be monitored with continuous EEG monitors. So these are monitors all over the patient's head, and they're designed to detect seizures and predictors for seizures. And these are not seizures where the patient's shaking. This is a seizure only in the patient's brain. So the only way to detect it is with the EEG monitors. Now, seizures are very common in these kinds of patients who are critically ill, and seizures can lead to brain damage. And in fact, this is so dangerous. The seizures can be even more dangerous than the original hemorrhage. And doctors will go to great lengths to try to prevent seizures, to the point where they give the patient medication to actually stop the person's brain from functioning so that the patient won't have a seizure and the brain will be destroyed. So anyway, we need EEG to detect these kinds of seizures. However, typically in hospitals, there's not quite enough resources to go around. So there's a lot of the EEG monitors stay on patients for way too long, and then patients who need them don't get them. So we need a better way to allocate these monitors so that we can better treat these patients, better serve these patients. All right, so what doctors would do, okay, they would go, if you have a patient and they're ill, you would have all these scoring systems available. And in fact, there's tons and tons of these things. So this is a website called Medscape, and it lists literally hundreds of medical scoring systems. So if you went to the category for neurology, which is over here, you'd find a subcategory called seizure. And then you could look at the 2 helps to B score. And if you click it, it would show you, the questions that the doctor would answer. So there's the 2 HELP and then S and then 2 points for the whatever. So anyway, that is this model right here. And then the doctor would fill in the points based on the brain activity of the patient, and then get a score. And then the score would translate into the risk for 6 hour risk for seizure. Now, this particular model is different than all of the other models in Medscape, in that it is actually a machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. It was built from over 70 variables, even though there are only 6 there. It's just as accurate as your favorite black box model on that same data set. It doesn't force you to trust it. Doctors can decide themselves whether to trust it. There's no additional explanation needed because doctors can really understand how all the variables are jointly related to form the prediction. And they can calibrate the score with information not in the database, such as, oh, you know, I'm looking at this patient, they have this extra thing, I'm going to add another point for that thing, and then that gives me a better indication of the patient's risk. Okay, so the way that 2 helps 2B was created is as a minimization of the following optimization problem. So there's 2 terms, the logistic loss, which keeps the model accurate and calibrated to the data. So this will allow you to get accurate risks, just like logistic regression. And then there's a model size term, which keeps the model sparse. So this value here is just the number of non-zero terms. This is a regularization parameter that trades off between accuracy and sparsity. And then there's an additional set of constraints, which says that all the coefficients have to be integers between -10 and 10. And it just so happens that the solution came out as 1s and 2s, but it could have come up with any numbers between -10 and 10. Now, this model is just this particular optimization problem. I would think that this is the problem that doctors would want to solve anyway when they're creating these scores, right? They want it accurate, they want it sparse, they want small integers. They would go to great lengths to get these integers, right? They would do all kinds of rounding and blah, blah, blah of logistic regression coefficients. But this is the problem I think they ideally want to solve. Now, this is a mixed integer nonlinear program where the feasible region is the integer lattice. So it's actually a really hard math problem. But I think this problem should be solved by computer scientists rather than solved by doctors, right? I don't think we should hand them our problem. I think we should solve this problem and help them. And so this is the optimization problem that we solve that created the 2 helps 2B score. The algorithm that we designed for doing this is a mixture of a cutting plane method with branch and bound embedded in it. So it's actually a pretty sophisticated optimization problem that actually allows you to solve this in a reasonable amount of time for real data sets. Okay, so now when the patient comes into the hospital with their hemorrhage and they get their surgery and the doctor is monitoring they're looking at their EEG signal, and the doctor says, okay, I'm going to look at the signal and I calculate that this patient has 3 points. And so they're high risk, and I would place them then on continuous monitoring for over 72 hours and start them on preventative medication. Now, so far, the 2 helps 2B score was validated on an independent multi-center cohort. I actually was not involved in the validation study. This was our neurology collaborators who did this study. And they have found that after it was implemented in several hospitals, that it resulted in a substantial reduction in the duration of EEG monitoring per patient, which allowed them to better allocate the monitors to people who might need them. And this allowed them to monitor a substantial number more patients. So over twice the number of patients they could monitor now than they could before. And this allowed them to help substantially reduce the amount of brain damage that were experienced as a result of seizures and to help them save lives. So that's an example of how interpretable models can work and can be implemented in high stakes settings, including in intensive care units. So I want to switch over then to the other extreme and talk about computer vision. Okay, so for computer vision, as I mentioned, the big challenge is really to figure out what the definition of interpretability actually is and how to actually get that embedded into our neural networks. So I'm going to present 2 ideas, and this is the first one. And so, so what does it mean? What does it actually mean to have an interpretable deep neural network for computer vision? Well, I want to start by talking about what it doesn't mean. And I want to just put up maybe you've seen this before today or something, but this is a typical problem with explanations of deep neural networks. a lot of people try to explain neural networks, but it doesn't really work very well. And that's because neural networks are not actually designed to be interpretable. So there's no reason why they naturally should be. And so this kind of explanation, this one kind is particularly bad. It's called an attention map or a saliency map. And it's supposed to give you the explanation for why this is classified as a husky. Okay, and indeed it highlights the right part of the image. Okay, so you think you understand the network, you think you might even trust it, but then you look at what else it's doing. And here I'm asking it for why the image has a musical instrument in it. And it gives me the exact, almost the exact same explanation. Okay, so it's just a, it's just not a good explanation method. It's telling you what pixels it's looking at, but it doesn't tell you what it's actually doing with those pixels. So our first approach to dealing with that is to use case-based reasoning. So case-based reasoning is kind of like K-nearest neighbors. It's like, this case seems similar to this other case I've seen before. It's kind of like what Dr. House does. I don't know if you guys watch that TV show, but I love that TV show. And you have a doctor on the TV show, and he looks at the patient and he says, that patient has a green foot. I've seen a patient with a green foot. He had chilblains, so maybe that's what it is, but also the patient has a weird heart condition, so he reminds me of this other patient who had a similar heart condition. So we wanted to get the neural network to try to reason like this. So we want to have the network reason about an image based on its similarity to other prototypical cases. So here is our prototypical network explaining to me why it thinks this bird is a clay-colored sparrow. And I like working on the bird watching data set because I don't know anything about birds. So anyway, it's going to pick out different parts of the bird and tell me why it thinks this looks like a clay-colored sparrow. So it says, so the network's saying, I think this part of the bird looks like this part of that bird. And this is a prototypical clay-colored sparrow. And I think this part of this bird looks like this part of that bird. And this is a prototypical clay-colored sparrow. And then this part looks like this, and this looks like this, and so on. And this is how the network actually reasons. And the prototypes here are learned. They are not selected by experts. They are learned. And the ways to compare images, that's actually learned as well. Now, because the neural network says this looks like that, and this looks like that, and this looks like that, we called the paper, this looks like that. And the main idea of the paper is that it adds, you take your favorite black box, and then you add an extra layer to the network just before the very last layer. And the layer does this comparison based on case-based reasoning and prototypes. And again, the prototypes are learned during training. So let me repeat that again. So you take your favorite black box. So here's your favorite convolutional neural network for computer vision. And then you create, you make it interpretable by adding this extra prototype layer just before the last fully connected layer at the end of the network. And we usually select 20 prototypes per class. And the number of prototypes that can be chosen as a parameter. And then the network in this layer, it scans the image looking for parts of the image that look like each of the prototypes. Okay, and so that's how it's working. All right, so let me give you a little more detail on what it produces. So the network is now going to explain to us why it thinks this bird is classified as a red-bellied woodpecker. So it takes the bird and it says, well, I think this looks like that part of this bird. And in fact, I think it's very similar. I'm going to give it a similarity score of 6.499. Okay. So I give it this is a very high score, by the way. So I think this is very similar to that. And then there's a class connection weight, which tells you how important this bird is to this class. So how much this image looks like a red-bellied woodpecker. Okay, so this is how similar my test case is to the prototype. And this is how important the prototype is. And then we add up the points for all 20 prototypes and get a score for the red-bellied woodpecker class. And we do that for all of the different classes. So here I'm showing you the same calculation for the next highest rated class, which is the red cockaded woodpecker class. But interestingly, red cockaded woodpeckers do not have red heads. And so it can't gather any points from the comparison of the bird's head. And so it just has to use the feathers. And it just can't get that many points based on only the feathers. And so it says, okay, no, I think this is why it's a red-bellied woodpecker. I get the most points for that class. Now, I'll show you an example where it messes up. So here, in this case, we started with a base model of DenseNet 161. We added the prototype layer, and it got this bird wrong. Okay, so this is a warbler, and it got confused as to whether this was a prothonotary warbler instead of a Wilson's warbler. It's actually a Wilson's warbler. Sorry, got it wrong. Okay, so it gives you some evidence for why it's a Wilson's warbler. It's looking mostly at like the eyes and like some aspects of the feathers. But the fact is, it actually really looks like a prothonotary warbler. I mean, I don't know if you can see this, but I'm looking at this bird's, face, and I'm looking at that bird, and they look very similar to each other. And so that explains why I got confused. So, all right, fine. Now, as I mentioned to you, I can choose any base model I want. So if I swap out the base model with a VGG16 model, then it turns out VGG16 actually gets this one correct. And if we look at what happened, you can see that there's certain information that it's not using. And in particular, the top of the bird's head. So as it turns out, Wilson's warblers generally have a black spot right on top of their head, but this bird doesn't. And so I think what's going on is that this might be a baby Wilson's warbler. And so as it turns out, baby Wilson's warblers kind of look like prothonotary warblers. And so maybe the network, maybe that's the reason that the network got confused. All right, so we've been looking at, comparing the accuracy of the prototype network to its base networks, to the black boxes that we started from. And what we found is that on this, and this is a benchmark data set in computer vision. This is one of the main benchmark data sets. This is where, high neural network performance was born, right, with this data set. And these are the accuracy levels that we get from the different base models. So a whole bunch of base models, we get accuracies between these numbers. And then when we put the prototype network in and retrain it, then we get numbers that are actually within this same range. And then if we take a whole bunch of these prototype networks and stack them, okay, so instead of a linear model at the end that's a combination of 20 prototypes, you get it, if you stack them together, it's more prototypes. It's still interpretable because you're still doing case-based reasoning. It's kind of a bigger network. But if we put them all together, we actually beat the accuracy of the black boxes. So what I'm saying is that even for the most difficult computer vision problems, even for the benchmark data sets, even for the places where the deepest of the deep neural networks were born, we can still have an interpretable model that has the same accuracy as a black box. So I'm going to switch over to a different notion of interpretability next. Okay, so I'm switching topics here. So instead of using case-based reasoning, I'm going to talk about a different type of interpretability for deep neural networks. So again, I'll start with explainability techniques, which seem to not do so well for this particular type of explanations. And that is to try to figure out what concept each node is detecting. There's a lot of people doing post hoc analysis on deep neural networks to try to understand what the nodes are doing. So there have been cases where people claimed that a certain node was like a grandmother node or like a lamp node. Like, the information about lamps, it's traveling through that node. That node is the lamp node. But I think a lot of the work in this area is kind of bogus. So people say, fine, what we're going to do is figure out if all the lamp information doesn't go through one node, well, maybe it goes through, multiple nodes. Like if you look at where all the lamp information is activating, It's some combination of node 1 and node 2. It's activating node 1 more than node 2, okay? And so people have been trying to do all kinds of summary statistics on these what they call concept vectors. Now, I claim that if you actually want to know what a node is doing, you probably should give it some instructions instead of assuming it's going to do what you think it's going to do. So that gets to the second approach on interpretable deep neural networks, which is to try to disentangle the neural network's latent space so that all the information about a concept flows through just one node. So this is what we call concept whitening. And I'm going to tell you about how this approach works. So as I mentioned, CNNs are not naturally disentangled. So let's say that what we really want is sort of all the information about airplane that the network needs for whatever it's predicting to go through just one node, and all the information about car just through one node, and so on. Okay, this is not what a typical neural network does, but we're going to create one that does this. Okay, so let's go back though. Before I do that, I'll talk about the idea of what a concept vector is and kind of why it doesn't work. All right, so let's say that we take a standard CNN, and I want to consider the latent space of the batch neuron layer. So what I'm doing is plotting the activation of each image, and I'm showing you kind of which neurons are activated and how much they're activated. And so this is kind of the idea behind concept vectors. Like you have, maybe these are lamps, and so lamps light up neurons 1 and 2. These are trucks, which light up neurons 1 and 2 as well. And then, this is some other thing. Now, what people often do, like I said, is they create these concept vectors that point toward the different concepts. But the problem with that is that these concept vectors don't really make that much sense because the lamp information might not be centralized in one direction. It might be all over the network as well. Also, you might have concept vectors that are kind of close together. Like these are both pointing in the same direction, even though they're two completely different concepts located in different parts of the space. So you kind of want to be careful about interpreting these concept vectors. Now, what we wanted to do instead was to try to disentangle the space by replacing the batch neuron layer with something that would disentangle the space. And in particular, we want it to whiten the space, so decorrelate and normalize it. So whiten it, and then afterward align the axes with the concepts that we're actually interested in. So now neuron 1 actually is representing all the information about airplanes that we actually are using to predict the outcome. And then neuron 2 is handling all of the car information. And neuron 3 over here this is off in some other direction, handling whatever other information. All right, so the concept whitening technique, it does really kind of funky things when you add it to different layers. Now, if you add it to a very early layer, then the network really isn't capable of producing the whole concept. So it just produces the information that it can about it. It creates kind of an abstract preliminary version of a concept, like kind of a rudimentary version of the concept. So for instance, if we're trying to predict airfields and we have a neuron in the second layer dedicated to airplanes, then it creates its own notion of what an airplane is in the second layer, which happens to be a gray object on a blue background. And again, we didn't tell it to do this. We told it, just route all the airplane information through this one node. And this is what it came up with by itself. And it's interesting because none of these are airplanes. They're all like sea creatures. But that's what the network is doing at the second layer. That's its most extreme version of airplane in the second layer. And then for bed, it created an abstract notion of bed, which is sort of warm colors, it looks like. And then for person, it seems to create some kind of interesting textures. And then, so in earlier layers, color and texture information related to the concepts tend to be represented along the axes because you don't really need to have a whole airplane to detect airfield. You just need sort of the part of the airplane that is like what it can represent in the second layer. On the 16th layer, the concepts are much more well defined because it actually has the capacity to represent airplane And it's actually using airplane information to detect airfield and bed information to detect bed. Okay, so it can be really interesting if you want to trace what happens over the layers for a particular image. And this one is really interesting. This is an image of an orange sunset. So as you know, this has neither a bed nor an airplane in it. So what's going to happen? So early on, the network says, well, it has kind of warm colors. I think it's a bed. I think it's got a bed in it. Doesn't have an airplane. No airplane, because it's not a blue object with a gray thing in the middle. So, okay. Great, so that's what it does early on. And then as the layers, as we move through the layers, it starts to think that maybe there might be an airplane in the image, and maybe not so much a bed, because it's seeing the blue sky and the clouds and so on, and saying, maybe I think it's more of an airplane. And then as time moves on, it starts to realize, wait, hold on a second. Maybe there's no airplane in that image. Maybe it's less of an airplane than I think it is. Nope, maybe it's more of an airplane. So it's like a race here. It's like maybe there's the bed. That's the airplane. It's the bed. But in any case, at the end of the day, it decided that it really does not have a bed in there. Maybe an airplane, but definitely not a bed. Anyway, so you really can get a sense of kind of the way information is flowing through the network and what the network is using, what information the network's actually using to make its predictions. Now, what we've noticed about CW is that we don't notice any sacrifice in accuracy over the black box that we started from with the batch norm layer. And the accuracy with CW is on par with standard CNNs. It's also very easy to use, because if you have your already trained black box and you replace the batch norm layer with the CW module, then all you need to do is one additional epoch of further training. So one pass through the whole data set. However, you do need to have training data to define the concepts for defining the axes, but you would need that anyway if you were going to do concept vectors. So that's not something that's unusual. And then again, a great benefit is that for free, you don't need to create concept vectors, because the concept vectors are actually the axes of the latent space. All right, so just to summarize what I've talked about in my talk, an interpretable model is constrained. It's a constrained model that helps you understand it better. And I've given many different definitions of these constraints, starting from sparse being sparse and having integer coefficients. Those are constraints, as well as forcing a neural network to do case-based reasoning in this looks like that paper, as well as disentangling the latent space of the network in the CW paper. So these are all different types of constraints that we've added. Now, as I mentioned, evidence does not support an accuracy interpretability trade-off. And I've given you examples in deep learning specifically to aim at this particular statement, where it's really unclear to me that you would truly ever need an honest to goodness black box, because even in these cases where we have the most accurate, the deep neural networks that are the most accurate for benchmark data sets, even in those cases, we can add interpretability constraints without losing accuracy. And obviously, there's the nuance that I mentioned. Whereas with tabular data, most methods perform similarly, so it opens the box up to being able to create very sparse models that are just as accurate. So the example I gave was scoring systems. And then with neural networks and computer vision problems and time series problems and other things, you have to define interpretability differently, but you can still get to where you want to go without losing accuracy. And I gave you, again, these two examples of where that happens. And so these are my versions of the extremes. So from very, very sparse models with integer coefficients that are linear, all the way on the other end to these deep learning models for computer vision. All right, thank you.